Hi everyone. So this is activity 1.3. You're covering this in week number 2. So remember, this is a required activity. So you will have to do this one along with me and bring it to the final exam for part of your grade. So in this activity, we're really looking at starting to graph some of these functions. In the last activity, you looked more about looking at these functions as a table of values. Okay, and a little bit symbolically. So this is going to look at these graphically. So you've graphed ordered pairs in 095 or previous math classes, so a lot of this will be review. We are also going to talk about what a discrete versus continuous function. And I caution you, whenever you're drawing something that came from a set of ordered pairs, to not always connect it, even though we tend to want to connect the points. Okay, here we'll talk about when it's appropriate, when it's not. So what we have here is, I started the graph just to kind of save some time on the video. We're going back to, if you look at page number 1, there was a table. There was in the very first activity, and it was just talking about how many cars are in a parking lot per time of day. So they wanted us to take that big table of values and just graph it. So that's what I've done for number 1 here. I've already plotted all these points. Okay. They're using the time of day more in military time, like 700, 800, and then it goes to 1400, 1600. Okay, so you do see there's a trend. Notice I did not connect these. Okay. A good rule of thumb is I would only connect the points if I have a symbolic representation, meaning I can write an actual equation I could plug in any number into that and get an output. And for here, I only had the list of ordered pairs. I didn't have an equation that went with it. Okay, so what you would want to do is kind of stop the video, go back to page number 1 and plot those points so you've got this graph in front of you so we can answer the questions from here. Okay, so there we go. Just, I guess, a quick little review. Make sure you realize that when you're graphing something, the input is always going on the x. So you see right here, I've got my input on my x-axis, and my output is always on my y. That's how we graph all functions. So for number 2, determine the practical domain of the parking lot function. Okay, so in this case, if I look at that table, my practical domain, the values that they use for this, it started at 7 o'clock in the morning, so we're calling that 700. And it went all the way up to 2200 in military time. Okay, so I'm not going to say all real numbers because this is not something where I have a function equation that goes along with it where I can plug in any x that I want. Okay, so it's only defined for this time of day. Determine my practical range. So that was my domain, my practical range. If I look at that table, all my outputs, I can't have any less than 0 cars. So it's 0 in the number of cars. So it has to be whole. So it has to be an integer, and all the way up to 600. Because they're saying that, assume that the capacity of the parking lot is 600, so I can't go outside of there. So describe any patterns that you observe in the graph. Okay, so I observe that, it starts off low around 7 o'clock, okay, and then the number of cars is increasing from about 7 o'clock until about 11, if I'm looking at that. Then it decreases and it starts dropping until about 4 o'clock. And then it grows again. Then it increases again until about 6. Okay, so we've got these little peaks in here, right here, and right here. Okay, so it increases and goes back down, and increases again and goes back down. Can the parking lot function be defined symbolically? So there would have to be some kind of steady, it doesn't have to be linear, but it has to be some kind of steady pattern here, which we don't see. We see some little patterns, but not something that I could write an equation for. So no, we can't write an equation for this. We can't write a set equation for this situation. This is why I am not going to connect those ordered pairs. Okay, because it's not defined for everything. It's only this set of ordered pairs. All right, so we're going to look at another couple situations, ones that we've looked at in the past, and do the same kind of thing and graph them. Okay, so here I have, I'm coming back to the example on activity 1.1 about the temperature in Lake Placid, and it's a function of the date. Okay, so what I've done already ahead of time is I set my graph on my input. Just ignore the phone ringing, I'm sorry. My input is on my x-axis, and that is the day, the date, and then the temperature is on my y-axis, that is my output. So again, this just came from page 2 on activity 1.1. Okay, so I plotted those points. And again, we're going to look at what is our practical domain for the temperature. Practical domain for the temperature function, sorry. So my domain and this one, my practical domain, I only use these dates, okay, only had outputs for 1, 2, 3, 4, 5, 6, and 7. So that's all the set of inputs that I have for that. And then my practical range for that, if I look at all the set of outputs, the only outputs I see on there is 23, and I'm ordering them from smallest to largest, no matter how they are when they're ordered. Okay, I'm putting them all in order from smallest to largest when I list them out. So even though 1 doesn't match with 23 and 2 doesn't necessarily match with 24, I still list them in order when I'm listing the set of domain and range. Okay, is this function discrete? Okay, actually, I think the beginning of my... Oh, you have to ignore those dots moving. I skipped over kind of talking about, I didn't see this definition here, what it means to be discrete. And that means that the function only works for these set number of values. It's discrete when we cannot write an equation to follow it, okay? So both this one with the Lake Placid temperature and the last one with the number of cars, they are both what we're going to call discrete. Okay, let me see if I can get my points lined up again. That should be right about. All right. Is it discrete? This one is discrete. We cannot write a function for it. In symbols. I'll say symbolically. It's only defined for this set of ordered pairs. It's not defined for anything. Once we write an equation for something, it means we can really plug in other values not on the original table of values. Okay, so let's move down. So we're coming back now to another one that we had looked at in activity 1.2. So look at this one. This one is defined with symbolically right off the bat. Okay, so this one was the marathon one, figuring out how many miles that you had left if you plug in a certain number of times. Okay, and that was, remember, you were running at a rate of 6.5 miles per hour. So on this one, you're going to see this is not discrete. We're going to call it a new name in a second. But what is the practical domain of this function? Okay, so my practical domain, we answered this, I think, in the last activity. I could only have from 0 to 4. I'm not going to write 0, 1, 2, 3, or 4 because it's really any real number in there. Oops. So it's any real number from 0 to 4. Okay, this one doesn't have to be a whole number. I don't have to plug in only 0 hours or 1 hour or 2 hours or 3 hours. I can plug in anything in between. So right there, that can tell you that this is not discrete. Okay, so I have actually just took any 5 ordered pairs. Okay, I plugged in 0, 1, 2, 3, and 4. Did I have to pick the whole numbers? Definitely not. I could have put in 0.5 of an hour or 1.2 of an hour, but I just chose those values just to make it easier to plug in. And so for each one, I plugged into the function, okay, and got my output, my distance from the finish line. So we're going to take a look at a graph of that.